Okay, a very good morning, everyone, and welcome to this next installment of the Iplex Tech Talk series. A really warm welcome back to those of you who joined us in our last sessions. And for those of you who may be joining us for the first time, a big thanks for dialing in today. We know your time is valuable, and we're really grateful to have you here. My name is Nathan Swaffer. I'm the National Marketing Manager here at Iplex, and again, I have the honour of stumbling through as your host today. A little bit of background, we kicked off this Tech Talk webinar series nearly a year ago now, and we did this to more regularly be able to share some of the experiences, insights, and learnings that our Iplex team have picked up over the many years as being a part of this wonderful water community like you all are too. And so it is a pleasure to be back today, and we'll be diving into all things polyethylene, which has proven to be a really popular topic. We've had a lot of you join us today. Now, just to flag, one key piece of feedback we've had from our previous sessions is that many of you out there in the audience would actually like these sessions to go a little bit longer, a little bit deeper on content, and with a little bit more time allocated towards the Q&A at the end of the session. So we've done that for today. So instead of wrapping it all up in an hour like we've done in the past, we expect the presentation itself to run closer to the hour mark, and then we've allowed around a half an hour for the Q&A, so a bit longer there. So around 90 minutes in all. We've given ourselves a bit of flexibility at the end. Of course, if you can't make the whole session, no problem at all. Our plan is to share a recording, all going well, in the next few days, so you can pick up on anything you missed, and we'll, of course, share that out to anyone who registered but couldn't attend today. So if you have any colleagues who got called away, we'll send out that link in the next few days. Now, we've found that your questions from the audience absolutely make the session. So please, at any time today, as the session is running, feel free to go up to the top of your screen there and click the Q&A box and send through your questions. And then after the presentation, we'll run that Q&A, and I'll pass as many as I can on to our presenters. And so, speaking of, without further ado, let's please pull up and welcome our expert presenters today. So as you've seen, build on the ticket, which is why so many of you are here, I'm sure. We're joined by Mr. Luke Kennedy, the Polyethylene Technical Product Manager here at Iplex. And we are really very honoured to be joined by an industry legend, Mr. Darren Chandler, Director at Gem Industrial. Gentlemen, thank you so much for joining us today. Now, Luke, you've been in the PE game for like over 30 years now, which is almost longer than I've been on this planet, and across various senior and technical roles. Now, I happen to sit across from you in our Iplex office here, and one thing, as I know just from hearing your world, is that you are living, breathing, talking PE day in and day out. But one thing I've never asked is, are you also eating PE resin for breakfast? Because it would not surprise me.
Well, thanks for that introduction, Nathan. I guess, although to be inert, I think there's better ways to find fibre in your diet. So
glad to hear that. And Darren, we're so thrilled to have you here today. We just couldn't talk about poly, particularly large bore PE pipelines, without digging into the hands-on, the installation, the project nitty-gritty. And mate, with over 20 years under your belt in this space, we're really lucky to have you join us. I think I heard you mention the other day when we were sort of planning that your team have installed something like over 40 significant pipelines. Is that right?
Yeah, that's correct, mate. That's correct. Thanks very much, Iplex, and thanks, crew, for having me on board today. It's great to be able to come along and present a couple of case studies for you, some real live installations. I guess it's one thing having pipe, and the other thing is getting in the ground. So no, we've done 1 metre and above, I think probably more than 40 projects. Yes, mate.
Thanks so much. Well, it's great to have you, and look forward to your insights a little bit later on. So that's enough of me. Without further ado, let me hand over to Luke, and he'll kick off the presentation today. Thanks, everyone.
Thanks very much, Nathan. I just wouldn't mind getting this up if you bear with us. Okay, so as Nathan said, this is Tech Talk. It's the series on large bore polyethylene pipes. I guess I am quite lucky, as Nathan says, that I have spent a lot of time in the industry in this particular material. And I guess one of the things when we thought about this Tech Talk is, what are the questions that we're being asked for? And right now, there's a huge amount of interest in larger sizes and thicker walls. We hope to bring you a little bit more content as to what's going on around that. Just bear with us. Nathan, would you mind just, for some reason, it won't let me go to the next slide?
Luke, yeah, sorry, mate. You've just got to jump in and take control of the pack.
For some reason, it didn't let me. Let's just try again.
Now, I will just share with the audience that whilst we build ourselves as experts in polyethylene, we're not claiming the same for technology. So thanks for your patience. You should be right now, Luke.
Thanks, mate. So today we're going to be talking about broken up into three major topics: the pipes, the fittings, and installation. I'm really looking forward to the installation side because there is a lot of questions that comes around availability of and constructability in the larger sizes of equipment and such, and it's just so lucky to have Darren here. In the polyethylene pipes, we'll be talking about the material, looking at the international trends versus the local trends, the resins, and there's a little bit of confusion about resin types at the moment, and then possibly what we're going to be doing is Iplex in the future. Then we'll move on to fittings, designing and sourcing of compliant fittings, and compatibility to existing systems, which seems to be at front of mind with designers right now. The pack will then finish with Darren giving us some case studies on some tremendous projects that he's been involved in. So on to the pipes. So what is polyethylene? Polyethylene is a long chain molecule with short branching. It's a viscoelastic material and it's semi-crystalline in structure. So that's a big, long-worded way to say that it holds characteristics of rigid pipes and flexible pipes. And the actual material itself is actually just a bunch of ethylene molecules. Poly meaning many, ethylene meaning many molecules. So 2 carbon, 4 hydrogen atoms in a long chain. So if we think about ethane or ethylene in its purest form, it's a gas. And as the molecules get bigger, you'll notice I've just got some pictures there of some petrol, some castor oil, some Vaseline, some candles, and then polyethylene. It's pretty much the same stuff. In fact, if you burn polyethylene, it smells like candles. The one major factor you might see in polyethylene is we have some primary additives, and that being carbon black. The carbon black actually gives it its UV stability, but without it, it does actually look like a opaque candle wax. So I'm going to move on to a really nice bit of a presentation that McElroy did for some years ago on polyethylene. We'll just run it through and just have a look at some of the actual material properties in action rather than just looking at them on a piece of paper.
A properly made butt fusion joint with polyethylene pipe produces a leak-free connection that is as strong, if not stronger, than the pipe itself. When a butt-fused pipe sample is subjected to a quick burst test, the failure point is always in the pipe wall and not in the joint. The burst pressure is usually 4 to 5 times over the pressure rating of the pipe. Under extreme pressure and tensile load, a butt-fused pipe will elongate and neck down before pulling the joint apart. Another advantage of polyethylene and the butt-fused joint is its ability to be bent to a minimum radius of about 25 times the diameter. This gives the advantage of eliminating some fittings in a system. The butt-fused PE pipe is also extremely tough and abrasion resistant. It can be squeezed off if required for repairs and re-rounded to its original shape. It is the most efficient, cost-effective way to join polyethylene pipe and is easy to do.
So thank you, McElroy. If I could just dissect that a little bit further, and I'll just see if I can get into it. What we're looking at here is a butt-welded piece of pipe that was overpressurized by about 4 times the actual pressure rating to get an instant failure, the pipe will always fail in a longitudinal burst, and it usually represents itself with like a ductile beak. We call it a parrot beak. That's a successful failure. So when we see that in the trench, we know that the pipe has most likely been overpressurized. The interesting thing is there's no particles that get away. There's nothing that shatters or explodes, which means that's why it's actually so safe. You'll also notice that it hasn't failed in the butt weld. It's actually failed in the pipe, and that's fairly typical of what we see. This is an excellent a picture showing the just the ability of the pipe to withstand tensile loads. And I think you'll see things like Christchurch earthquakes and Fukushima. There's been a couple of papers talking about failing infrastructure, and it's of particular interest is that polyethylene had pretty much 0 failures, where other rigid pipe systems, of course, did separate and suffered from what you would expect. The ability for us to actually bend straight pipe is something that's actually quite underutilised in Australia. I must admit I'm involved in the actual range and the product management, and when I see requests come in from site for like a 10-degree sweep bend or a 15-degree sweep bend, I'm immediately on the phone to the estimator or salesperson saying, can you please kindly make contact with the customer and see if you can use the actual bending radii of the pipe, just so that way you can save yourself a couple of welds and a fitting, which are quite expensive. If we move to the next slide, talk about the actual sizes and the pressure ratings that we actually come across. At Iplex, I'm sure a lot of you know that we represent a lot of manufactured products as well as bought in. We have our PVC range, we have our ductile iron range, and we also have GRP pipes. We also compete against mild steel pipes in Australia. So when you look down here, it's a little bit hard to see, but this is 2 metre OD pipes to give you some form of context. And up here, we're looking at about PN20 to PN25. I think people are quite surprised when they see that polyethylene is from 16 mil now up to 2 metre OD. And it just gives you a bit of a feel as to see how we seem to be, used to be 10 years ago, PN10, PN16 pipes. We're starting to encroach up into the PN20, PN25 space regularly and in the larger sizes as well. So if we take a look at what's happening around the world right now, some of you might be surprised to know that there's actually polyethylene smooth wall pipes being extruded in pressure up to 3.5 metre OD now. And of course, Australia is the largest extruder at 2 metre OD right now. Some of the wall thicknesses we've seen is up to 150 mil internationally, and we have reached 130 mil in Australia. And it seems like there's pressure even more and more to keep going up. Just on that too, it might be worth mentioning that a lot of fittings can be manufactured from a hollow bar. Some of those hollow bars in short form to make fittings can be up to 300 to 400 mil. So, there's a lot of interest in just how thick this stuff can actually be extruded. Materials. Internationally, PE100 is definitely a very popular resin, but the RC or stress crack resistant variant of PE100 seems to be actually starting to emerge a lot more. In Australia, we're more stuck in the PE100 world, and that's a very safe world in itself. I'll cover that why a little bit later. Fittings availability, we're up to 3.5 metre OD. Right now in around the world, so there are actually fittings being manufactured and actual welding equipment to actually do that, and we're at about 2 metre OD right now, and that seems to satisfy the local market. Polyethylene applications, of course, are gas, water, wastewater, industrial, electrical, comms, and it goes on from there. And of course, we're the same here. So the adopted resins are PE100 and PE100RC. Resins in Australia that seem to be also emerging are PE100, PE100RC, and PE112. So just to give you a bit of an idea of some of those expressions, because we're trying to cater for people with a basic level of polyethylene exposure to also those designers that are quite into these resins on a daily basis, so please bear with me if we back up to basic form. But you might have heard of PE50, PE63, PE80, PE100, PE100RC. Then we have a RT version, an RD version, PE112, and then the mystical PE125. Today we'll be talking more so about the PE100RC and the PE112, just to give you a little bit of context. But these older resins, if you ever see a specification with PE80 on it, that is now a redundant material, only because of the superiority of the PE100 suite. So when we look at actually the consumption of these products in the Australian market, the comment to make is 95% of all resins is still PE100. And why? It's because it's a bloody good material and it's proven. So when we get into some of these other materials like RC, RD, RCD, PE112, we're starting to get into subsets of a PE100 resin. The PE125 I have left up there because we are asked about it every now and then. It's anticipated that PE125 might not be at a commercial sense offered to the global market for maybe another 5 to 10 years. So why would you do a PE125? It just means that every time you increase your material strength, you reduce the amount of wall thickness. However, there are compatibility issues when you come to doing that. So please bear in mind when we're talking about these other materials that they only represent a very small part of the market. So the thing to remember, and this is compliments of a company called Quinos that has since pulled out of Australia. Quinos was a resin supplier, Australian made, which unfortunately has now been disbanded, but they had some terrific technical content, so we borrowed that from them. But I guess this slide is what it's trying to say to us is, if you have a PE100 resin, and if you try and say, let's make the MRS stronger, so make it a stronger material, that potentially you might be pulling back some of the other materials in the property that it can do. So resistance to slumping and extrusion, that's the bit that helps out Iplex when we're trying to manufacture a pipe. So if you pull in one direction, there might not necessarily be an advantage in another one. So we will talk about a couple of these resins a little bit later on. Disinfectant resistance, there has actually been some press about some failing polyethylene pipes in some very hot climates. So there are some resins that are available that have some better resistance towards that. Stress crack resistance is what we're talking about when we talk about the RC grades. Rapid crack resistance is something you see in incredibly cold climates, so sitting negative 30 degrees where some sort of impact may actually cause a rapid crack. We just don't see it in Australia. Raised temperature. There is raised temperature resins available offshore, and it just hasn't really seen much of an interest in Australia. But I thought we'd put it up there anyway, just so if you do actually get some sort of niggling, what was that about, you know where to turn as far as coming to see us to get further detail. But moving on to the RC, which we are seeing a lot more inquiries about. It was developed in the early 2000s, so it's actually been around for a little while. And how RC material works is it actually retards what we call phase 2 of crack formation. So just to explain that a little bit, this little diagram here, again, thank you to Quinos, was just a little representation of what occurs when you actually have some sort of crack. So at phase 1 here, let's assume that we've got, say, let's just say a tardy contractor has put a rock directly facing into a pressure pipeline. So, of course, that's going to cause a stress concentrator. This is the phase 2 here, where we call void formation and crack initiation. In this void formation phase, you get these little, you get the long chain branches, the short branches on the long chain molecules. They start to get these little microfibules that join and they start to separate. After a while, you will get a crack initiation, to which then you will get the actual crack propagation. So that's the failure point. The interesting thing, and this is in polyethylene PE100 as well, that from time of the actual damage to the time of the actual failure of the pipe, 60 to 90% is actually in this void formation and crack initiation phase. And so how these RC materials work is it's in the branching, the short branching, they actually have a little bit more of a molecular bind. So, and look, the actual testing on them is absolutely unbelievable. So back in 2011, Iplex and Quenos developed a brand called Millennium Pipe. You might have seen the term HSCR material. So that was the Australian version of an RC pipe. So HSCR, high stress crack resistant pipe, ended up being something that we had marketed in Australia from about 2015-16 onwards, and it had reasonable uptake, but we're not certainly seeing the amount of interest in this material as we are with the RC right now. So there was an actual piper guideline written about that. For those of you who don't know, we've got Plastics Industry Pipe Association of Australia, which actually represents all of our industry participants, from resin manufacturers to welders to certifiers to people like ourselves. So POP 16 is now going to be made redundant. POP 16 actually covered the HSCR, which was like the Australian version, and now we're falling in line with the European RC grades. And the reason we're doing that is, some of you are familiar with international grades will know that EN 12201 for water and EN 1555 is for gas, does actually have this mention now as a material. So some of the interesting things about the RC grade, for those of you who know about the notch test, which is one of the ones we perform on polyethylene pipe, we say loosely 10% of the wall can actually be scratched, damaged, affected in some form before you will actually consider that the pipe will have to be derated or fixed or transformed or something. So when we actually pass the we put the notch pipe test in for standard pipes, we take 20% of the wall away, and then we introduce it to a stress at 80 degrees of 920 kPa. And what we do then is we actually test it to failure. And what we request is we need it to last at least 500 hours. That's a very standard test. So to pass as a conventional PE 100 material, which does have stress crack resistance in it, it needs to pass this test for 500 hours. The interesting thing when we were doing the testing is we're getting results greater than 5,000 hours. So it's a monumental change in the resistance to stress cracking. So what does that mean though? If you can take 20% of the wall, it just means in this phase, the notch pipe test, it was having 10 times the longer time. That doesn't necessarily relate to pressure resistance. So please bear in mind, we're only talking about pipes that may be damaged. So where would that be something that would be of interest? Absolutely something like a directional drill. So let's just say a significant directional drill has occurred, trenchless installation, and I don't know if you're aware, but sometimes there might be some sort of rock impingement or something which has scratched the surface. Conventional thinking was that if the pipe has any damage any more than 10%, then it might be compromised and may need to be subject to deration. With this material, there is an argument to say that there's a little bit more flexibility in the amount of damage it can pick up. And to give you a little bit of reassurance on that, they actually did 30%. So they almost took a third of the wall out of the actual polyethylene pipe. And then they did the same test and it still lasted 2,500 hours. So it sincerely is a good resin. So when we talk about PE112, PE112, instead of being a 10 MPa material, is an 11.2 MPa. So just to round off, say it's 10% stronger. So it is a higher MRS material, but the interesting thing is this resin is only popular right now in sort of Oceania region. So we're talking Asia and Australia. So it's got limited acceptance in Europe and the USA. So although Australia hears a lot about this resin, there isn't actually much exposure offshore. And of course, this means that there's actually no international standards that actually cover this off as its own standard. We usually have PE 100, we had PE 80, and I think the industry is waiting for PE 112. So as a designer, because of the higher MRS, it might be possible, however, to actually consider reducing the wall thickness for the same pressure by leveraging the MRS. And there is actually a place in the standard that does allow for that. However, it absolutely must be said that Australian Standard 4130 was not written for the actual PE112 material. So all we would say is careful evaluation is needed before you do. But where would, say, Iplex use something like the PE112? We have that in our dye reduction suite that we do on behalf of Interflow. Interflow have a material called TightFlow, which makes up part of their ReadyFlow suite. And that's where we actually reduce the OD of the pipe and pull it through failing infrastructure like asbestos, cement and such. So that's where you've got the PE112 pipe, instead of it operating as just a coating or a liner, it's actually an independently fully pressure-rated system that's designed. And why we would use the PE112 is we would use the advantage of the 10% reduced wall, so that way we get the better flow. So, and I don't know how many of you are aware, but there's 40,000 kilometres of failing asbestos cement in Australia. So you'll start to see products like this come into fruition soon. So we'll just move on to PE fittings. We're going to briefly touch on electrofusion, butt welded, fabricated, mechanical, extrusion weld, and compression. There are a couple of others, but these are the main ones, and there definitely has been some advancements in these. So on electrofusion, we know it's a reliable jointing system. It's proven. It's typically used in the smaller sizes, and I guess when we're a 2 metre exposed company, smaller sizes to us is in reference to, say, 315 and below. And it's especially used in difficult locations where you might have troubles getting a butt welder. There are some sensitivities around hygiene, and being very blunt with the market, 99% of all failures we see in electrofusion has to do with the actual preparation and just lack of quality control measures around the actual welding. So when it's done correctly, it is absolutely a fantastic way to join pipes. It is fully pressure rated, and it's considered fully restrained. Because you have a homogeneous line with only contact of polyethylene, you don't need thrust blocks and such when using it. What you're probably not aware of is the availability is now up to 1400 mil OD in couplings, and there's companies even going further. We can actually do saddles now, tapping saddles up to 500 mil OD off takes, which is quite big when you see them. And the other thing to remember, and I've got a picture of this, is we have the ability of getting butt welded fittings and putting tails on it to make it able to be electrofusion welded any time at all. And Iplex does have a fabrication unit that can do that. Sweep bends can now be EF welded. Previously, because it's a post-form process, there were some questions around whether or not those ends were true. However, all manufacturers now usually have a guarantee, and Iplex certainly does have electrofusion capable sweep bends. Butt weld, we actually know it's a reliable joining system. It's typically preferred by installers just due to the cost advantages, particularly in the larger sizes. And it's also fully pressure rated and fully restrained. Recent advancements, we'd say 5 years ago, that 800 mil fittings was considered pretty big, whereas now we're fielding inquiries for 1600 mil, 1400 mil, 2 metre quite regularly now. So the market has significantly jumped up in interest over a very short amount of time. Just for interest, we do own a 2 metre butt welder that could be mobilised. We do have large wall, thick wall contractors available, such as Gem Industrial, and there are a considerable amount of butt welders up to 1600 mil OD in Australia. So I've heard a few rumours that you can't get butt welders above 1000 mil, but that's actually not true. And just as an example of that, Darren, he probably won't even have it in his pack, but he's just bought a 2 metre butt welder as well. Because he's currently working on an 1800 mil job that he probably can't share today because it's under confidentiality, but there's a live job in 1800 mil occurring in Australia right now. I think pictures speak better than Luke Kennedy does. So I'd just like to give you a couple of examples of innovation. The bottom picture here shows a butt weld fitting that we've welded tails on so that you can actually put electrofusion on. The reason I put that is I've had a couple of instances where we've heard inquiries go offshore for long spigot fittings that someone needed in a relative hurry, whereas we could have just welded pipe on each end to make that capable. The next picture is of a tapping saddle. It's actually got, it was an instance down the Gold Coast where they needed some air valves, and they didn't really want to put on the air valves themselves. So Iplex put the air valves on. So just to give you an idea, we didn't actually have those air valve, the actual heads of the electrofusion saddles in stock. We air freighted them. Each one of those saddles for an 800 by, I think it was 3-inch or 4-inch offtake, weighs about 2 kilos. So we just airbagged them from overseas. It was so quick, and I think it was only a few days before we actually provided those to site. One of the ones you're probably not aware of is these things here are called a flex restraint. We call them caterpillars. They're an electrofusion fitting that you can put around the outside of a pipe just to make a thrust flange. So if you're on site and you might be on a hill, you notice there's a bit of water on the embankment and such, and you think, oh, we could probably do with a puddle flange on here on site. It's a very rudimentary ratchet strap that hangs, puts a few of these on. For each side, you use a few more, and you can actually make yourself a puddle flange. Now, the interesting thing about that, and we'll talk about it a bit later, is one of the problems we've always had in polyethylene was the perception that if someone puts a post hole digger through a pipe, it's virtually impossible to fix up. Someone, and it wasn't us, came up with the idea that if you use a stainless steel wrap, it's always been a temporary solution. The reason for that is it's not thrust restraint, and it's actually can move as polyethylene expands and contracts. But someone came up with the idea of putting a couple of these flex restraints over it to make these mechanical joints actually fully thrusted. Now, we will have some, we'll have discussion about that later on. But what that means is so let's just say I live in Brisbane. So Unity Water up here has someone puts a post hole digger through a 500mm main. Before they'd say, what should we do? We'd say immediately use a stainless steel wrap like a wang clamp, ABK repair clamp, but maybe come back to it later on after the emergency, and then you'll probably have to cut it out. Whereas now possibly you could just use this. Some of the butt weld innovation examples is we've got so much to show you, so cramming all these onto the one slide is makes them a little bit tiny. But just so you know, that's a 1400mm fully rated T. It's a billet T, and it has an 800mm one, and of course other ones around there as well. We've always had problems with 45-degree junctions being subject to significant derating. However, with this new way of doing it, where they're using thicker billets and they're using the reducing factors of fabricated fittings to come up with fully rated fittings. So that's a very wordy way to say that we can get 45-degree junctions fully rated. And we have done things like high pressure FLTs for up to PN25. Well, that one might have been PN32. And you can see a few exciting types of manifolds there and such. So another one that's actually of interest is with polyethylene, we've always struggled a bit to get true tangential Ts or scour Ts. Now, of course, with the billet machining, we are actually able to now get fully scoured Ts, and these are actually starting to take off a bit. The stocks in Australia aren't great on these, so only because it's supply and demand. But I think that once people understand that you can actually design true scours into your pipelines, we'll see a lot more of this starting to come in. So fabricated fittings, moving on. Fabricated fittings can be made out of a combination of electrofusion, butt weld, and extrusion welding. And it is a versatile accompaniment to more complex designs. One thing to remember about fabricated fittings is they can be subject to pressure derating. The availability of fittings now is up to 2 metre OD, and in fact we can, at Iplex Brisbane, we can actually manufacture fully rated mitered bends using the Piper Pop 006 derating, because we do them on a shallow angle of 15 degrees, which means more sections. However, they are fully rated. We can actually get fully rated tees now up to 1600 mil OD. And there are companies right now working on up to 2.5 metre OD. We also do CNC routing of flat sheet, and we've done some pretty, unfortunately I can't show you, we've got some that were under subject to confidentiality, but we've done some amazing things with our CNC sheet bed, and we can actually source PE sheet up to 150 mil OD. So when you combine all those things, and I've got a few photos to show you, it's really impressive how you've got to think of polyethylene now more like a general engineering shop. Pretty much, if you've got something in your design, and there will be subject to derating depending on some of them, we can pretty much get it out, whatever it is, the container doors. And with mechanical fittings, they've been used for years, and possibly they've only been used in the smaller sizes. They are fully thrusted, and there's some pretty exciting fittings that are available to the market, and I've got a few examples. So here's some of the fabrication examples we've just picked up over the years that we've recently done. This was a vertical stem for landfill. It was done out of, I think it was 1,000 mil P16 pipe. These were manifolds done to the coal seam gas industry. They're called a slug catcher, and they're the last bit of piping that goes into a compressor station that actually catches moisture out of the gas wells before it goes up. And the interesting thing about these are they were 1,200 mil P16, and I think they were, yes, that's right, and we had 1,200 P16 fittings air freighted in from offshore because it was an urgent project, and it could be could be considered fully rated. That one there is an 1,800 mil mitered bend, and Darren will talk about one of the projects that actually went on later on, just to give a bit of context. Some catch pits that we've recently done, they've done using extrusion weld, and if you notice, it's got a significant amount of reinforcement, and that's an example of the sheet with extrusion welded, and there's some butt welded fittings and such there. This one here was for Port Augusta. It's actually 1,000 mil offtake, and the interesting thing about this one is we had to do it to the tolerances within millimeters, which is quite challenging. And also it had offtakes of 500 mil and 315. So that's where we used a combination of butt welded fittings, mitered fittings, bends, as well as electrofusion saddles to come up with that design. That's an example there of a 15-degree rated segmented bend, and that can be considered fully pressure rated. So if you notice, even in our catalogues, we will have, say, a 90-degree segmented bend with only 4 sections. That would be subject to Piper Guidelines 0.8 derating, whereas if you do this like in the other sections, we can absolutely do them to fully pressure rated. And that might be something that you might consider if you needed S-type or 3-dimensional configurations in a wash plan or something versus a typical sweep bend. Sweep bends can actually, if they've got left in the sunlight and such, they can move by a few degrees. So if you need sort of rigidity in your movement, absolutely something you'd consider. So something I'd really like to dwell on today, and I think it's something that as an industry we need to bring to the forefront of options with respect to joining as well as repair, is we all know the repair clamps. ABK repair clamps are an EPDM mat, and they have a stainless steel wrap, and they're designed for the post hole digger. What people don't utilise a lot in Australia are couplings like the Super Plus coupling. The Super Plus coupling is designed like a gibbo. The only difference is it's designed to go poly to poly, and it can be used to join fully thrusted and long service live. So let's go to the post hole digger concept again. Unity Water have a 315 mil line, and they know it's actually had a post hole digger through it. Well, piece of pipe and 2 of these couplings, and you've got your whole repair system. So the next one is the Super Maxi straight coupling. I'm a big fan of these fittings, and interestingly enough, we find it difficult to promote these in Australia. And the reason is they're significantly more expensive than the coupling sitting next to it or the wrap. Now, the way to consider these things they are a repair system. They're designed to do any rigid pipe to any rigid pipe. So if we go back to the post hole digger through the 315mm for Unity Water again, let's say that they know they've got a 300mm main somewhere. They don't know what type of material it is, but they do know the rough size. If you have two of these fittings and you grab any rigid pressure rated pipe, then you have your full repair system. And the interesting thing about these is they are actually available up to 800mm OD. And we do try and push these whenever someone has an actual project and where there is sensitivities or there is something where they want it to try and have it. But because the cost of them is sort of compared in the procurement side against these things, they tend to say that they seem to be a nice to have rather than a must have. I'll leave you with the thought again that it really is something that as an industry, not just for polyethylene, for piping repairs, having a couple of these on your inventory, even if it's just a temporary repair, or you can leave them for a long-term solution. So the extrusion welding, I don't know if you're familiar with it or not, but it's typically it's like a soldering. So it lays down an extrudate at a certain amount of temperature and heat, and we reinforce it with gusseting, which would be cut on the CNC machine. But also be aware it is subject to derating, but it is actually quite common in Australia and rural applications to use them. The compression fittings, recent advancements, we're absolutely blessed to have Plazon for our compression range, and we actually have Fusion Plast backing us up on our electrofusion molded and other fittings as well. So Iplex do bring to the forefront some internationally renowned brands, and Plazon is certainly one of them. We did get a question through the pre-submitted forms about water connections, so boundary connections. Plazon's just developed a Plas saddle. So what Plas saddle is it's actually a saddle that goes around a piece of pipe, and it can actually just come off in a thread, so you can go to your normal TPF&R, or it's actually got a compression fitting or a threaded fitting. But the interesting thing about this is there's no metallic parts in this actual saddle at all. The actual connection goes over the pipe, which means you can install it from a fully installed pipe, and it's actually got its own cutting mechanism in it. So after you've put that saddle on your pipe, you can actually wind that down and wind it back up, and it'll actually take the token out with no swarf, and you actually have a live connection. So we do have interest from water authorities on these right now. We don't have them on the shelf right at this moment, but I would suggest within 12 months, as soon as people see how quick these are to put on these pipes, it's an innovation that will just grow just because of how it does. The other thing is too, Plazon have designed these for Series 2 PVC and OPVC pipes as well. So I can answer the market, the testing is done, that these do work on PVC pipes, and there's always been questions about, saddles and such on such pipes, but it's a really good innovation. Couple of things that have hit me in product management for technical assistance is just want to have a quick chat about loose flange adapters versus nominal flanges, or some of you might have heard it called maxis. A stub flange adapter is typically what we've used in polyethylene pipe for many years. And the difference between an adapter and a full face or nominal flange is that the actual nuts and bolts go through the actual face of a full face flange, whereas with a stub adapter, the bolts go on the outside. So the reason that polyethylene pipes were like that in the old days was when the pipes were PE type 50 material PE type 80, they didn't have as much stress crack resistance as they do in these days. So someone much smarter than me deduced that if you cylindrically bore holes out of a stub flange face, it might be a crack propagation point, particularly under immense stress. So that's when these things were formed. Look, as far as usability of the stub flange adapter, they're fantastic as long as you have interfacial pressure enough that you can actually compress your gaskets under the nominal amount of pressure. So why I flag that is poly to poly, where the surface is absolutely constant, is fantastic and it's easy to calculate. Where you might get into a little bit of trouble is if you're going to a ductile fitting or something where the actual sealing, the sealing surface of the pipe may not be 100% of the adapter. You just got to be a bit careful there that you do have enough. And I won't go in it today, but we certainly would like to bring another tech talk around calculating torques, bolt torques, flanges and such. And I will mention later on that we actually have software that will assist you with that. So look, we are still a big believer in stub flange adapters. The civil industry has taken to these nominal flanges, and I would assume it's because they do look like more of a conventional fitting. The difficulty with them can be that obviously with polyethylene pipe, viscoelastic material that might sort of, if it's in the sun, it might bend forward because it might expand on the surface, and where it's not expanding underneath the trench and such is, you have to have absolutely deadly alignment on your actual bolt holes when you're actually hooking up to something. So how a contractor on site might approach that is, he might do that bolt connection up to his valve, and then he might butt weld his pipes onto that, whereas it's just a bit more difficult. It's just worth mentioning that you do get a lot more flexibility with a loose backing ring, because if it is that the alignment is slightly off, because the backing ring can be manipulated and there's no need for alignment, it can actually provide some advantages. So, look, I'd take up the rest of your day if you get me started on bolt flanges, keeping your bolts tight and such, and grade. So if anyone is interested, I absolutely do have further information on that, because the science should say every bolt connection should really be looked at as its own certain entity. There's a lot of misunderstanding when it comes to bolting and configuration of polyethylene pipes. And the one thing to remember is we have a lot, the polyethylene pipe itself, if you compress it too much, it can go into creep mode, which means that your bolts can go loose. But I'd like to talk about, if anyone is interested in the topic, we've got a bunch of information on that. The other thing we're seeing a little bit of is mismatches of polyethylene pipes to conventional materials. We've got a live example right now that we're working with someone on site where it was a 450mm PN25 pipe, which has significant wall thickness, and they're matching it to a 450mm PN35 ductile pipe. So the thing to sort of understand is there's a significant difference in the ID of those pipes. So I guess with polyethylene being one of the only pipes that you talk about in OD, I guess the message is always consider the ID of your pipe, especially as we go into this world of larger bores with thicker walls, because the mismatch in obviously the hydraulic flow on that would be terrible. And so for us, if someone was going to ask us for a 375mm ductile pipe, we would recommend the 450. So for the 450mm pipe, it possibly should have been a 560mm. If the hydraulic flow is the thing that you really want to be aware of. So I'm almost out of voice, and I tell you, this part of it is going to make the reason for you to being here today. So I'd like to hand over to Darren. Darren Chandler has worked with Iplex for many years and seems to be at the forefront of all the complex projects that we've done in the larger sizes. And I think his part of it will speak for himself. So over to you, Darren.
Thanks very much, Luke. Thank you. If I can take control.
Sorry, everyone. Sorry, Darren. Sorry, Luke. I'm just going to jump in there just very quickly. I've just had a couple of people reach out. They just can't see the presentation on their screen. I think it's isolated. It's only been a couple. But what we're going to do in the back end, Robin's just going to pull the screen down and pop it back on to hopefully just loosen up the system if anyone's having trouble there. So we'll just do that for one moment. Once that reshares, Darren, will let you take control again and you're off and running. So we'll insert some banter here for a few seconds. Give you a moment. So to interrupt your flow.
Well, maybe Darren, talk about your new 2-metre machine.
Okay, and we're back.
There you go, we're
Thanks,
up.
Darren.
All right, so I can take control now, guys? Yes.
Yes, please.
Righto. Thank you. Look, thanks. Firstly, thanks, Iplex, for having us on board here today. We are humble and we appreciate the invitation to come along to present some of the installations that we have installed over the years. I selected a couple of installations to talk about today, mainly in the large diameter thick wall pipes. Some of them are older installations, as you'll see. Some are back over 10 years ago. But I just want to give some understanding that, you know, large diameter pipes and thick wall PE pipes have been being installed in this country for some years. We are a small company. We're located in Victoria, not far from the beach, down near Inverloch or Phillip Island. We work in most states around the country. Currently, Western Australia, bit going on in Western Australia, New South Wales, Queensland. We've even done some work in New Zealand in past times. We've always been keen on polyethylene, got involved in polyethylene through the local milk factories. We did some work for some of the local milk factories being in Gippsland a long time ago when we ventured or stumbled across polyethylene. We stumbled across electrofusion couplings, and then we stumbled across butt welding at around about the same time, 2008, somewhere there. There was some lack of water in our region. The water authorities came to us and said, look, we need to find some water. Can you assist? We found some water in bores and in rivers and in creeks, and we built pipelines across the hills and around the roads and so forth to get water back to the treatment plants to continue to survive. So that's how we really got into polyethylene. Luke mentioned earlier that we have completed approximately 40 projects above 1 metre and thick wall or thereabouts. He also mentioned we're working on a current 1800 millimetre pipeline at the moment. It's fairly confidential. I can't talk too much about that, but maybe sometime in the future we'll be able to. It's a very, very interesting project. We completed a 1600 millimetre project back in 2012. You can see the 1600 millimetre machine in the middle of that photo there. We flew that machine in for a disaster. I'm going to show you a video of that disaster shortly. And that's how we really got into the large diameter thick wall installations. Currently employ around 20 to 30 staff. We've got a number of PMs. We've got some estimating guys and also some office admin. We'll flick across to the next slide. Now, this video, this really just sort of shows a project that got us in the game with a large diameter pipe.
But first, fears tonight that the state's power supplies could be under threat after the Morwell River broke its banks, sending floodwaters rushing into the Yallourn open-cut mine.
What was supposed to be a trickle turned into a torrent. A diverted section of the Morwell River bursting its banks, sending water gushing through a tunnel. In ruins, the conveyor system that transports coal to the power station, and water filling the open-cut mine that provides more than 20% of the state's power.
Meanwhile, engineers are being confronted with the massively challenging and expensive task of working out a way of plugging the banks of the river.
Flooding of the Yallourn open-cut mine presented a major challenge for engineers to divert the Morwell River. While a temporary dam and dewatering pumps were installed, a permanent solution for diverting the Morwell River was required. This could only be achieved with polyethylene pipe. Engineers decided on a single large pipeline that would take the entire flow of the Morwell River, reaching up to 800 megalitres per day. That required a 3.8 kilometre long, 1600 millimetre wide pipeline to be installed very quickly. PE 100 was the material of choice because of the harsh installation conditions, ease of local manufacture, and its ability to be produced in the large diameters required. Due to the size of the pipe and the tight tolerances which had to be supplied, the market-leading melt strength of Alkadine HDF 145B from Qenos made it the only PE 100 up to the challenge. The excellent dimensional tolerance reduced installation time as the pipe could be easily matched for welding. PE 100 pipe was manufactured in Albury, New South Wales and Welshpool in Western Australia, delivered to the Yallourn site where the 12-metre pipe lengths were welded into 120-metre pipe strings and dragged into place. Once the pipe strings were in place, they were welded together, completing the 3.8 kilometre pipeline diversion. The Morwell River was successfully diverted within 26 days, allowing the power station to get back to full capacity and thus securing Victoria's energy supply. Alkadine PE 100, engineered to outperform.
Yeah, okay, so that's really got us in the game, I suppose. Large diameter, thick wall project. So the Morwell River itself was a man-made river. It was relocated to allow for more coal extraction within the site. A fairly large site, I mean, the site's probably 8 kilometres square, something like that. When they removed or moved the river closer upstream, that river became quite flat. So they had some quite big levees on there for massive flood events. In these circumstances, there was some water that got down through the bottom of the river. It got down into the tunnels. There was 4 tunnels underneath the river that allowed coal to be moved by conveyor underneath the river. What happened was the water got through into that tunnel and it broke the bank out. As it broke the bank out, all of that water was continuously running into the old mine, what they called the old mine or the old township field, which is where Yallourn was located. When they moved this river back upstream, this 3.8 or 3.6 kilometre section of river was very, very flat, about 2 metres of fall over that 3.6 kilometres. So consequently, as the river burst its banks and water was running into the mine, water was coming from both angles. So it was coming downstream, but also coming back upstream out of the adjacent river. So this was the first diversion we completed. We've since completed another diversion on this site, but you can see the 1600 millimetre pipe on the right-hand side of the river. It was an urgent time frame, obviously. At the time, there was so much water going into the mine, the concern was shutting down the whole site. They shut down 3 turbines and 3 boilers out of the 4. So we lost 75% of Victoria's power pretty much overnight. The concern was the electrical system within the mine was lapped at the door by water. So we maintained some flow by dewatering. So we dewatered the actual mine. So we're sort of talking 100 metres below the surface. We built about 40 kilometres of 500 and 560 PE, and we got pipe from anywhere we could get our hands on it. At the time, Iplex were very, very good to us. They supplied everything they could, and they extruded minute by minute just to keep that 500 and 560 pipe coming along to dewater. That effectively was just buying time. It didn't get us anywhere really. It just bought us some time, about $100,000 worth of diesel a day, just to run the dewatering pumps. Whilst we were doing that, we were negotiating which way, or discussing which way we actually divert the river long term. We had a 900 mil, so this was back in 2012, we had a 900 millimetre McElroy Trackstar at the time. It was our first larger Trackstar. We decided that we wanted to build 900 mil pipeline and then continue, get one operational and so on, do another one, so on. The engineers of the mine said, no, look, let's go as big as we can. And so we talked to Iplex. Iplex were able to get 1600 extruded very, very quickly. They also had the 2 lines at the time, Albury and one in Perth. We were able to bring pipe out of both locations. We got our hands on a 2-jaw McElroy fusion machine. One from over the west, the PIHA at the time, had a 2-jaw machine. We hired that machine along with a couple of their crew. Their crews worked day and night to build 120-metre strings of pipe for us. In the meantime, we air freighted a 1600 millimetre 4-jaw machine across from Chicago. Isco Industries at the time were great. They found a 1600 4-jaw machine for us in Chicago. we were able to air freight that overnight. So a 10-ton machine, it cost approximately 120K to get that machine here. The weather at the time was obviously major flood event. It was dismal. We worked day and night, 24 hours a day, 7 days a week to build the main pipeline along with the dewatering systems. So stage one, 3.8 kilometres. Large bore fittings were available. We had to have some stubs and rings. Mainly, there was no real bends because of the urgency. The mine actually fabricated some steel fittings, so we needed many stubs and rings. Luke spoke earlier about flat sheet and machining. Iplex built some stubs for us. I think around 20 from memory, something like that. So 20 stubs and rings of 1600 millimetres. We've now completed a second stage for Energy Australia. Things moved again on the MRD, so the man-made river, a couple of years back, 2 or 3 years back, and we continued with about another 7 kilometres of 1600 over there then. So in all, we've probably installed over 10 kilometres, of 1600 PN8 SDR21. Both pipelines are permanent now. There's a massive pump station feeding these pipelines. It's just the river's still alive, and the river will continue to run, but just to repeat flows. Around 800 lengths of pipe we used, around 800 truckloads, 1 pipe per truck, and 800 fusions. So all in all, I guess you can clearly see that was a 120 metre string sitting on the trailers there. We then pulled that 120 metre string into position with dozers, and then we used the 4-jaw McElroy machine to do the massive tie-in welds. The photo on the right shows a area where we couldn't build a pipeline, so we couldn't get access. You can see all the earthworks performed there. So we located our welding machinery up the top end, and we pulled that 1 kilometre string through on rollers with dozers. So we weren't able to get in and do tie-ins at that location. Moving on a little bit, this is an 1800 millimetre job we performed a few years ago. It's only a small or a thin wall pipeline, but regardless, a very large diameter. It was the result of a concrete pipeline failure. So there's a concrete pipeline already in existence, been in existence for about 7 years. The lifting lug within the concrete had failed and there was a massive leak. So this one wasn't super urgent, but it needed to happen. So once again, polyethylene was the great choice here. I will say though, like early on, there was no space available for this pipeline. You can see the site on the bottom photo there, very, very tight, very sensitive environmentally. Our client had to build some earth and some structure, so push back into the lagoon effectively to build some earth, but then they could dig the trench, so then we could lay this 1800 pipeline. The original pipeline went straight under the middle of that lagoon. So the pipeline ran under Clearwater Lagoon, and the effluent that was going through this pipeline was leaking into that clear water. Urgent repairs, what was kind of urgent, it needed to happen. Minimum space, we had to find land and find space to build this thing. Given it was 1800, we only owned a 1600 at the time. This was probably 2019 approximately. So we only owned a 1600 millimetre machine. We have quite a great relationship with McElroy in the States. We venture over to their infusion conference, not yearly, but as often as we can. So we knew of their 2000 millimetre Talon. At the time, McElroy had a 2000 metre Talon sitting in their shop, and we were able to hire that from them for this specific project. It was freighted across for the project. Photos there, you can see it in the background. It's quite a big item, about 28 tonne in total. Very different machine. You don't need to lift pipe into the top of the machine. The actual machine lifts pipe off the ground. So I've mentioned it was very thin wall. It was around 54 millimetres thick, I think, from memory. So the tough part for Iplex was to extrude pipe that large, but without sag. So it was challenging for them. Became very, very good pipe. That was really, really cool. So around 800 metres in total length. We needed some fittings, so we needed some 90-degree bends. But given, number one, the talon couldn't get around a 90-degree bend because it lifts the pipe from the bottom, we couldn't track around. It would have been craneage to lift the talon off the pipeline whilst we were building the pipeline. We talked to Iplex about the 45 degrees. So Iplex built some 45-degree bends, which Luke showed earlier. They were large enough to get the talon to rotate around, but they were also fully rated. So they were able to come up with many segments. You see the bottom photo on the right there. We had 2 bends on 1 truckload. It gives you a bit of an idea of how big those things were. Yes, we constructed those. The urgency of the fittings, obviously, as urgent as the pipeline. We made the fittings from the parent material, and the only other connections were really to, given this was a drainage system, they were to concrete manholes, most ends. I think there was about 3 or 4 concrete manholes in the project. We used puddle flanges and extrusion welding of puddle flanges and then cast into concrete each end. So this is a little bit thicker again. So it's a 1200 millimetre pipeline, but SDR 11. So it had a wall thickness around 129 millimetres. Yeah, tough, a very, very tough site, really tough site. So I guess these projects, I've tried to give examples of probably the most challenging projects we've had. You know, it's pretty easy to go along and get a couple of lengths of pipe for a civil, for a subdivision or something like that. You know, you might get some 355 or some 450 or so forth. It's easy to weld it together. It's easy to find space and so forth. But when you get to some of these really big, ugly projects, I've tried to give some examples of some really difficult installations just so that you can see that they are possible. So this one, for sure, was very, very, very much limited in space to build the pipeline. We built the pipeline in behind, if anyone knows the Gold Coast and SeaWorld, I think we all know that. There's a spit just down the back of that section there. We built this pipeline along the spit, so we shut down the roadway and the end of the spit. The end of the spit was our construction zone, as that photo was on the left there. We built a 900 millimetre pipeline, a 900 metre pipeline, around 400 tonne in total. The reason this job was polyethylene, number one, was we had to move the pipeline in its entirety once it was built. So that 900 metre string had to be moved down the river, but it was also a directional drill shot, so a HDD shot. The HDD shot ID, around 1600 millimetres. We floated this pipeline once built. We obviously pressure tested it on land first. We shifted it downstream, and then we pulled it back onshore where we could and directed it to the entry hole of the directional drill shot, tied it on, and then pulled it back through. So a massive feat. This one was huge. You can see the boat, or the tugboat, pulling the pipeline offshore. That was us at the top spit from our site. You can see the photo up on the right-hand side there of the tugboat getting back to shore down the far end, and then you can see the photo on the bottom right of the excavators guiding the pipeline into the hole. The pullback. So once we connected to the drill rig and pulled back, took around 30 hours. So slow and steady. It was a very, very tough job. Really, really tricky job. We obviously pressure tested the pipeline once it was installed, and we completed the tie-ins both ends of the pipeline once it was in place. This one's a little smaller in diameter, nevertheless still quite challenging. So the North Connects tunnel in Sydney, there's a pair of pipelines installed, not real big, as I say, 630 and 225 SDR9, but once again, very, very challenging, not much space. It was difficult to turn the lengths of pipe around in the tunnel. One pipeline was utilised for groundwater around the tunnel, and the other was utilised for water coming into the tunnel. We pressure tested, and these trenches, we didn't excavate the trenches, but given they're in the bottom of the tunnel and the bottom of the mountain and the hill, there was so much rock. The excavation was immense just to make space for the pipelines. Really cool job, tricky. Lack of access into the tunnel. You can see the condition of the tunnel here, the mud. We also completed the riser coming back out and up to the tanks. So the machinery in the tunnel, the diesel fumes, the ventilation systems that we were around all day, every day, the noise. Very, very muddy and wet, but really, really challenging job, and one that we remember well. Another one, not a great diameter, but quite a thick wall thickness. It's a bit hard to see here. So this is Ocean Grove in the background, and the pipeline went from Point Lonsdale to Ocean Grove, around 5 kilometres. You can see here the drill site. So this is a HDD shot again. 2 large shots in particular. One around 2.2 kilometres and the other just under 2 kilometres. You can see this is our welding site. I think you can see my mouse, but the welding site down the bottom of the screen. Moving forward, that's a 20-ton excavator. It's pulling the second string that we built along the same thoroughfare. So we built one pipeline in up to the entry hole, and then we continued. You can see there's 2 pipelines here being built. Looking up to the next circle, the red circle, that's another 20-ton excavator up there. That's where we turned the pipeline around. So the pipeline actually went up and closer to the town, turned back on itself 90 degrees, well, actually 180 degrees. And then we tied onto the drill itself. The circle out on the green shed, that's actually a buffer tank for the effluent. So this project, you can clearly see the groundwater was the issue. Very, very wet. The ocean's just here. Very wet, extremely wet. Everywhere we went under the ground, within 6 inches, 150 mil, it was dewatering. So it was directional drill HDD project. Number of drill shots. I think it was about 4 shots in total, but the biggest or the longest one was 2.2 kilometres. And the shortest one, 1.9 kilometres. Sorry, the next largest was 1.9 kilometres. Pipeline was debeaded. We used Trackstar T900 to build the pipe. We turned the pipeline 180 degrees on itself during the backfill, during the backpull, and we completed all of the valving and air valving and scour arrangements and so forth on the pipeline, the project. That's really about all I have for now, and I think Nathan's going to jump back in and wrap things up a bit.
Okay. Thank you, and I'll pass over to Luke to run through a couple of slides, and then I'll jump in on the Q&A. Thank you very much, Darren. Okay, Luke, we've nearly got some slides coming up for you, mate, and you're just on mute to let you know. That age-old trick. Alrighty, Luke, you can take control, mate.
Thanks, Nathan. 2 secs. Just seems like there's a bit of a delay. There we go. All right, to close out, we probably spent a little bit longer than we thought on the technical discussion. So just before we do, I'd just like to make you aware that Iplex does invest a lot of time in bodies like Piper and such, but we're particularly proud of Iplex Pocket Engineer. There are a lot of people on this call, and a few people are actually registered, but I'd encourage you to take that QR code and register yourself, because we do have structural design tools, hydraulic design tools. The one I'm passionate about is the flange bolt torque calculator, chemical resistance and such, and we've got a building CAD library. That was one of the Q&A questions to say. Iplex has invested, we have a draft person, and we are trying to get through our catalogue. But we'll address that question as well later on. We'd also like to launch our new Polyplex polyethylene catalogue today. So it was actually published last night, and particularly for this tech talk. What I'd like to be able to say is that it's going to be more in line with what the discussion is today. Larger bore, thicker walls, and it does have a suite of different types of fittings and configurations that will be more in line with what is available. When we're thinking about Iplex, we'd like to say that, at the project planning stage, specification, project delivery, and post-installation and support, we're always happy to jump in at any stage of that. And what we do notice is that, particularly when we're getting into this new space of the larger and thicker, at the project planning stage is probably where I think we have some really, really good resources, including qualified sales engineers. We do have a few product managers lurking around that have been around for a while. We definitely have an exceptional project delivery team. We really do good jobs of complex deliveries and supplies. Obviously, we spend an incredible amount of time on our certification quality system. I'm part of a team that meets twice a week on any quality measures or product measures whatsoever, and it's a cross-functional team. And I've not ever seen a company put so much investment into ensuring that we do comply. And we're, of course, got our own laboratory supported by a NADA certification. So here's some of our sales engineers, which some of you may know. We're on the east coast of Australia, so we have Don, a very experienced engineer based in Victoria, as well as Thomas and Andre's up here in Queensland. And if anyone's looking for a career jump, we're currently looking for a sales engineer for our New South Wales division, which would be fantastic to see a few more applications. But feel free to reach out to any of us. Darren's also made himself available, and I can speak, and Darren's a very humble person and he won't like the acknowledgement, but Darren has helped out so many designers and such over the years with no commercial obligation whatsoever. He truly is an industry icon, and I see him at all the Piper meetings. He goes offshore. He's totally traversed through all the welding standards and such. So a very, very reputable company. And Glenn is also available in his estimations manager there as well. So we'd just like to say thank you. And that was a long session, and I know it was wordy and we had a lot of information in there, but I do prefer pictures, and particularly Darren's content, really gives you an idea of just where polyethylene ends up in Australia. I think we'll move over to the question time now, Nathan, and take control.
Thank you so much. And this will be really great. We've had some excellent questions come in, both during registration. Thank you, everybody, for that. And throughout the session, we've got a few more. So I know we're running up against the clock, but we do have time to jump in. And of course, if you do have to drop off, we'll have the recording a little bit later. And we'll also ask our team to respond to you directly if we don't get to it. So rest assured, you'll have some support there. Luke, can I throw you the first question? Could you talk a little bit more, please, about the long-term effects of different types of reticulation disinfectants and the risks, and separately the risks associated with gripper type fittings, please?
Okay, all right. So we'll take that in two stages. The most popular disinfectants in Australia are chlorine and chloramine. They're used to disinfect pipelines. There has been instances in small pockets in Australia where there has been some failures of pipes not necessarily lasting as long as they had. So there's a couple of things here. The first thing is chlorine and chloramine for disinfectant is a popular type of disinfectant. We're working with Sydney Water at the moment, who's got some incredible technology now where they're using ozonation instead of using that. And the reason for that is they tend to, whenever you do super flush a line after you've installed it, you then actually have to treat it as contaminated waste, the water, whereas the ozonation you can pass downstream. So that's quite an exciting technology. But in those pockets where there has been some degradation of polyethylene material, we see a combination of factors. The most important one is temperature and overdosing, where World Health Organization has a certain amount of disinfection that you are allowed. Obviously, we all know that there is actually sterilization, some forms of chemicals in our water and treatment. Where we see pockets in northern Australia, particularly Western Australia and Cairns, in smaller sizes, we have seen some failures. But it's really important to say that for pipe sizes above, say, 75 mil, where you don't have as much concentration in the wall, we don't see the problems anywhere. And there is actually PIPA guidelines do actually cover this in PIPA POP 018. So if anyone is interested in digging down on it a bit further, I'll make myself available, as well as have a dig at POP 18, because it will go into ORP values and way to determine it. But mostly the document does clearly stipulate where there might be a problem, where there's not, and it is in really small concentrated areas. Okay, on the gripper types, gripper type couplings are a mechanical joint, and some of them use different ways of actually joining. Some use little teeth, some use axial rings. There's all different types of mechanisms. I think the most important thing from a polymer point of view is to understand what that impression is, what it is as far as cyclic dynamic loads, if there can be any actual movements and such which may force more of a dent. Look at that 10% as far as the indentation. But the most important thing I would say is just have a think about what we went through today as far as RC materials, stress crack resistance. So as the evolution of polyethylene gets better at handling RC, then you can see that the type of failure that, if there was anything that was untoward, would be something to do with the actual gripping function. However, as the walls are getting better at resisting any of that sort of issue, then we can't see any problems. I think these companies are fairly well regarded. We use ABK, and of course ABK is a global. Anything you see from ABK mechanical, is proven.
Great. Thank you very much, Luke. That's a great answer. Darren, could I throw to you now, mate? Could you just talk us through a little bit more around the considerations and I guess key limitations you think about when you're looking to bore much larger pipes, say around that 710 plus range? What are the key things going through your team's mind?
Well, I guess normally if it's a design project and it's designed as a HDD, it will come to us in that manner. I mean, one that comes to mind, not quite that big, but one that comes to mind is a job we're looking at currently. It's only a smaller diameter project, about 500 millimeters, but the drill shot immensely goes pretty well vertically to go under a river, and then it needs to go almost 90 degrees to come out the top of the hill behind the river. So very, very tough drill shot. Location for us to build the pipeline is probably our concern. A driller of that scale would be a good driller, somebody that's been around, somebody that really gets it. There's drillers and there's drillers, but a driller to do a project like that would need to be the best of the best. For us, we're looking at space, really. If it's a drill job, normally you're going to find that, unless it's like the water table issue, but if it's hills or sensitive vegetation or whatever it may be, we're looking for space to build the pipeline, test the pipeline, and then after the pipeline's pulled in, then obviously retest and connect. So for us, it's not too bad. It's just finding space.
Yeah. Okay. Thank you.
And that means handling it.
And I imagine the criticality of controlling site conditions would be a key factor as well.
Yeah, look, as you've seen in that True Energy project, there was one section you could treat as a drill shot, that one section of 1600 millimeter pipe that we built 1 kilometre of. We left the welding unit in the one location and we pulled the string 1 kilometre just purely because we couldn't stage and tie in at that location. So we had to pull the 1 kilometre string out on rollers. We were able to get an excavator in there just to lift the pipe off the rollers, but there was no space to get a welder in there.
Okay, thank you.
Given the terrain.
And I guess just to throw you one more while you're there, do you have any discussion or thoughts on concerns raised around using fast fuse in construction, given maybe some still haven't adopted that out there in the industry?
So my understanding is we have used fast fusion before on projects, very much a project-specific requirement. Probably doesn't quite meet the POP 003 standards that we stick to, but coal seam gas have adopted the fast fusion technique. It's a process that was developed by an independent manufacturer. It was consequently used on a McElroy machine, the North American arrangement, where artificial cool air is injected onto the pipeline to artificially cool the pipe. Whether there's benefit in that or not, I don't think so at the moment. So I know McElroy did some research into this a couple of years ago. McElroy being a machinery manufacturing company, they obviously want to sell machinery. So when they looked at this themselves and thought, look, there might be an opportunity to sell some machinery here, when they did their actual investigative work, they found that 90% of the strength of a butt welded joint was created in the first 10% of the time, of the duration of the time. So what they found was if they better utilise their electronics and their data logging techniques, if we looked at the ambient temperature of the air, the temperature of the polyethylene as well, we could use a technique called optimised cooling, which was in effect no machinery sold, but there was more technology. So there's no allowance for that within the standard, as I understand. It's only to the ASTM standard. We have utilised that a little bit in this country already. So obviously we have low pressure fusion, which takes about 100% of the wall thickness of the pipe. So let's say we've got 100 mil of pipe, a cooling time for low pressure will be around 100 minutes. A high pressure fusion is about 42. So about half, let's say half the cooling time for high pressure. But then if you go to optimised cooling, you might save another 25% on top of that, given the ambient temperature of the day and those effects. So I think that will come. We're working on a project at the moment where the client's requested some opportunity around optimised cooling. So we're looking at that. But as I say, we've used it, we do it. We've got data logging equipment that'll cater for it.
Okay, thank you very much.
Awesome.
Now, we've had actually quite a few questions come in on this topic. So, Luke, I'll throw this one your way, mate. Could you talk a little bit about pressure derating of the fittings? And I guess the question is the best way to factor that into the design process, but also is there a construction method that allows the fitting to actually be fully rated?
I think the best bit about this discussion is the introduction of new innovation on products, because of the fact that where we say going back 15 years ago, we might have been using fabricated fittings which were subject to derating. We now have a lot of these billet and injection molded fittings in the larger sizes and thicker walls. So anytime we're using a billet, you can consider it fully rated. So there's two ways to answer this. In the fabrication equipment where we're using a bend and tee maker to manufacture a fitting, we're still subject to deratings. But let's just say for some reason we didn't have a billet available and someone needed let's say 1,000 mil P and 10T in a hurry, we can actually use the derating of the thicker wall. Piper guidelines, give you these guidelines. Piper Pop 006 will give you the published derating, and let's say a P and 8 1,000 mil pipes required. If we've got some 1,000 mil P and 16 pipe, then we are still able to fabricate something in a hurry. And what we will do then is we will use the ends of the pipes, we will route them down to match the P and 10 pipe. So you'll have a little bit of loss of hydraulic flow, but it is actually possible to use leverage the deratings. And I think we had one of those pictures up there where you saw the 45-degree junction, and they went the opposite way. They probably had an SDR sort of 4 pipe, so a really thick pipe, and they've used the deratings to do the same. So we've got so much more flexibility these days on this topic.
Yeah. Thank you very much. And one I'll throw to you, Darren. Do you have any commentary on a concern, I guess, that at the moment in regards to finding experienced welders, that we've got a shortage in Australia? And is this any particular risk that we should all be mindful of in the industry? Have you seen anything like that?
Yeah, I guess from our point of view, I mean, our business is probably the lumpy sort of style of business, being projects. We see that lumpiness around the government, I guess, and as funding's available for bigger projects, as the population increases, as we need bigger effluent treatment plants and water treatment facilities and so forth. So we tend to float along with those lines too. But yeah, I mean, we're in a small country town, so we're located in a town, and we work all over Australia. But it's we need to mobilise regardless. If we were in the city, we'd still have to mobilise to Brisbane or whatever it may be. So we're in a small country town, so we tend to get more locals, I suppose, that when we can bring up through and train. But you are right, yeah, definitely. I think today we're seeing a lot of those issues with a lot of industries, whether it be plumbers or builders or housing construction or whatever. I think we're seeing many issues. So not directly related to us, but in the form of more houses, more pipelines, more treatment plants. So unless you want to come in, I can get you on welder, mate. No worries at all. No,
I don't know if I've got the laptop hands to do a good job for you. Thank you. Now, everyone, we are coming up to time, and there's been a flood of questions. I'm sorry we probably won't get through them all. So what we'll do is we'll certainly go through those. We'll respond to them and send you a direct correspondence with an answer there. With that, can I just give a really big thank you to both Luke and Darren? You've both put in a tremendous amount of effort today to share your insights, and your commentary is just invaluable. So thank you very much. With that, we'll just close out with one last couple of pieces of detail I'll put up. And here we go, presentation. Thank you, Rob, my key assistant in the room here with me. We'll just jump to the end. So as I mentioned before, okay, sorry, and there was just a typo on our earlier slide there for Glenn's email for the GEM team. So I'm just resharing that with the correction. So Glenn is spelled G-L-E-N, in case you took a photo of that, not G-E-L-N. Thank you. And I just wanted to highlight, this is a series of webinars. So our next session, if you're interested and you found today valuable, will be on our GATIC range of product, and we're going to focus specifically on multi-part covers. Our GATIC team assists lots of customers who find that can often be challenging to specify or purchase or install. So they'll deep dive into their range and then the specification of multi-part covers. As I flagged at the top of the session, we do listen to your feedback and tailor these sessions to sort of make sure we're providing you the best value. So if you do have a couple of minutes, it's a really short survey. I do ask you to please scan the QR code, give us some feedback, good or bad. We'd love to hear it, and we'll just keep improving as we go. So once again, thank you for your time. Thank you for dialing in. We know it's really valuable. Thanks, Luke. Thanks, Darren. And we'll see you at the next Tech Talk, everybody.
Thanks for the opportunity. Thank you, everyone. Bye-bye.
Thanks very much. Thank you.